you'll have had your 3 consecutive desired symbols, not one. Okay, so if you're in this state, so that means the present and the previous symbols you've read are both ones, zeros, and then you read a 1. Well, then you're in this state. Okay, and then once you've found your desired substring, not 1. Then just stay there, just stay in that state. So it doesn't matter what you read after. If it's a 0 or a 1, you just stay in that state, okay, until the end, until you finish reading your substring. And since you're in the accept state, you'll finish in it. You'll with certainty you'll finish in it, because it doesn't matter what you read, whether it's a 0 or 1, you just keep staying there. And so you'll finish in that state. So the end state, your final state, is therefore an accept state, and therefore you will output the decision accept. Right? So that's the end of our second example of designing an automaton. Okay. Now we start. Now things, like, it's almost like a watershed here. You know, we've done enough theory now. You know about automata, you know about languages, input strings, states, transitions, formal definitions, 5 tuples. All that. We've got enough theory now that we can start doing stuff that's a lot more substantial. So I suppose you could argue that here is a kind of frontier, a boundary, an imaginary boundary line. And that's just me saying, this is not Sipsa. So above that is sort of junior level, okay? And now, so like here's the frontier in a sense. And from now on, it's debatable. I mean, you may not agree at all, but it's just me talking, my opinion. We shift gears a bit. We're getting now to senior level, right? Things will start getting a bit harder, more abstract, more powerful, and well, my view, more interesting. Right? You can start doing more interesting, powerful stuff. All right. Okay, so we talk about a new idea, a new topic. Now, so the key word here, or key phrase, is regular operations. Now, what are they? Now, you know about regular languages, and you probably remember the definition of a regular language. It's just some language that gets recognized by some automaton. Right? As simple as that. That's all it is. Okay? So in other words, there's a bit of revision here. Every string, input string, in that language is accepted by the automaton. Right? So if you put all the strings, all possible strings, in that set, and each string is accepted by the one particular automaton, then that string of all those, that set of all those input strings, that set is called a language, and the automaton that accepts every string in that set, that means that set is the language of that automaton, right? Or turned around the other way, you can say that automaton's language is that set of strings. Okay, so that's a regular language. Now, what starts being talked about here now is you can start manipulating, you can start operating on one or more languages. Right? So you're performing operations, you're making changes to, in other words, you're operating on languages, plural, or one or more. There are certain operations you can do on one language, So that operation would be called a unary operation. There are other operations that operate on two languages, two sets of strings, and that would be called a binary operation. Okay, so now a regular operation is one where there are a series of operations that allow you to manipulate strings, so languages, okay, regular languages. And so now in the next session or two, the next session I'll introduce three concrete operators that act on regular languages. One is unary, it just operates on one language, and the other two or three, are binary. They operate on two languages, right? Operations. Okay, so let's see. So these operations, they're part of a toolbox that help you to understand better the properties of languages, properties of automata, that recognize those languages and whatnot. Okay. Now, so it was starting to talk about that. So we're building up now a kind of toolbox, a set of techniques to manipulate languages. And this toolbox will, for example, including this toolbox, besides these operations, and it'll become clearer next session, where I'll give three concrete examples of regular operations. And I still haven't defined yet what's meant by this. But so regular operations are operations that they operate on, they modify, change. They operate on regular languages. So think of this as operations on regular languages. And such operations are called regular operations. And I'll give you three examples in the next session. Okay. Now, so these operations, they're part of a toolbox, sort of techniques, if you like, that you use to study more the properties of languages and automata. Okay? Now, it's still a bit vague, but this will become clearer as we go on. Now, to make an analogy, there's one quite interesting point here. Okay. Now, with this toolbox, with these operations, it will become clear to us that there are some languages that are non-regular, that they're not regular. Now, I raised this point as a question a couple of sessions back. So all this talk about regular languages, does that imply there are languages that are not regular? In other words, a regular language, remember that there's some automaton that recognizes it. So I guess then, by modus tollens, if you remember that, if there exists a non, is it tollens or ponens? I have to think. If there are non-regular languages, then I guess that means there are languages for which there is no, by definition, there is no automaton that recognizes them. Right? So maybe there's some properties of certain languages such that there's no automaton that can recognize them. So by definition, that kind of language would be called non-regular, or maybe irregular. I don't think that term's used. Okay, so by using these regular operations, these tools, these operators that operate on one or two languages, we will have more theory. We'll build up a toolbox that allow us to show that there are some languages that are not regular. In other words, some languages have no automaton that can recognize them. Interesting. Right? So starting to get more and more into the theory of what can be computed and what can't. Right? So it's starting to get interesting. Well, my view. Right. Okay. Now look, by analogy, if to make things a little bit clearer, and also make a very strong statement. So by analogy, what is the essence of mathematics? What is math doing? Now, one possible answer to that question is it's talking about numbers. Mathematics is all about numbers and manipulating numbers and applying operations to numbers like adding, multiplying, stuff like that. Right? So the core, the basic objects, if you like, of math are numbers, okay, and operating on those numbers. Now, by analogy, in computer theory or theory of computation, what would you say is what are the basic objects of theory of computation? Would you say they're bits, bit strings? Well, according to Sipser, the answer to that, well, his answer to that question, a lot of other people, I dare say, would say the same. The principle, the core, the essential objects, things that computer theory is dealing with are in fact languages. Languages. In other words, sets of input strings. Right? That's the assertion. Now that's a really important statement if you think about it. Right? Like the heart of computer theory, theory of computation, is languages. Okay. Well, whether you agree with that or not, maybe put it at the back of your mind and come back to it after you know a lot more and see if you agree with it or not. But anyway, that's Sipser's view, stated in the text. Okay. Right. So the main object of theory of computation, languages. The tools that you use to manipulate these languages, modify them, operate on them, if you like, regular operations. And so next session, start off with a definition. I'll give you 3 such operators, regular operators, that perform so-called regular operations. All right. Okay, so I'll stop there and move on.